One of the really cool things about chirality is how it relates to biochemistry. And so I've drawn a few biochemical compounds that we can look at and understand the chirality. The first one is glucose, D-glucose. All carbohydrates have the formula CnH2ON. That's where the term carbohydrate came from. So if you look at glucose, it's C6H2O6 or C6H12O6. Now, this is the structure of open chain glucose. Now, if you look, it's drawn as a Fischer projection. So there are four different chiral carbons. This one's not chiral because it has two H's. And of course, this sp2 carbon is not chiral. Now, the D of D-glucose means that this carbon right here, which is called the penultimate carbon, because you usually number this 1 through 6, is always fixed in this configuration. So all naturally forming carbohydrates or sugars or saccharides have this configuration at the second to last or penultimate carbon. So it's always good to practice R's and S's. One thing, if you want to count this, according to Kahn-Ingold-Prelog, an aldehyde is counted as a carbon attached to two O's and an H. So instead of a double bond to an O, it's counted like this. So now when we look at this carbon right here, oxygen gets the 1 because oxygen beats carbon. The top carbon is two O's and an H. The carbon below is an O, a C, and an H. So the top carbon gets the 2. The bottom carbon gets the 3. And since this H is coming out at us, it's the opposite of what we see. We see S. So this is R. As you go down the ring, always, you need to check, but always the top carbon of the two choices will get the 2 and the bottom one will get the 3. So oxygen gets 1, hydrogen gets 4, 2, and 3. So the second carbon or third carbon down is an S. This is an R, and this is an R. So glucose has the configurations RSRR, and the R configuration at the second to last is the one that stands for the D. Now, in most bio books, glucose isn't drawn like an open chain Fischer projection. It's drawn like this, which is a Haworth projection, where this is the ring flattened out and coming out at us. Now, if we wanted to know which carbon is which, I'm going to number it in blue for the way we usually number glucose. So the top carbon is the aldehyde is number 1. That is this carbon right here. 1, 2, 3, 4, 5, and here's that bottom carbon. Now, if you went and did R's and S's on all of these, 2, 3, 4 would match R, S, R. So this would be R, S, R. You can go and play with this molecule in your head and make sure you can see these are R, S, R. Now this one, the bottom one, is also R, that's the D. So whenever you draw a sugar, you're going to have this CH2OH going up. Now this carbon right here, this one comes from number 1. It's called the anomeric carbon, and it can either go up or down. I like to think of it as going same side, it's the same side as the D, or opposite side. So if it's the same side as the CH2OH, then it's beta. So beta starts with a B, which is a consonant, and same side starts with the an S, which is also a consonant, and that will help me remember that beta is same side. If you think up and down, you're going to get it wrong. So the alpha will have this one down. Now, of course, this is the Haworth projection. I'm going to go and draw a chair because I like chairs a lot. Traditionally, I'm going to put an O there, and if we go through and put in beta D glucopyranose and go and draw all the substituents, you will see that all of them are equatorial. So beta D glucopyranose, pyranose just means six-membered ring, has all the OHs equatorial, therefore is the most stable form of glucose. The next two sets of compounds are drugs. They are called Nsaids, or non-steroidal anti-inflammatory drugs. They both act the same way, and if you look, they have very similar structures. The first one is ibuprofen, or Advil, or Motrin. The other one is naproxen, or Aleve. Now, if you look, there is one chiral carbon in this molecule. I have drawn the S enantiomer of ibuprofen. If we number this, this would be 1, this would be 2, this would be number 3, and so you can see that this is S. Now, ibuprofen is sold as a combination of both S and R. The R enantiomer of ibuprofen is not active. So it's not active and it's not harmful. So they just sell it as a racemic mixture. Even though only 50% of the molecules do what you want them to do, at least this R doesn't do anything bad. Now, with naproxen or Aleve, and I believe it's sold as a sodium salt, so the H is taken off and replaced with the sodium. They only sell one of the enantiomers because the S enantiomer does what they want it to do, and the R enantiomer is toxic. And so this is a drug that's sold as only one of the enantiomers, whereas ibuprofen is sold as a racemic mixture. And the last structure I have is a very familiar structure of a steroid. Steroids all have 3 6-membered rings linked together like this, plus a 5-membered ring. And cholesterol has this structure with a double bond and an OH and these methyl groups and this big long R group right here. If we count up the chiral carbons in this structure of cholesterol, we'll see one here, one here. This one isn't chiral because it's an sp2 here and here. This one and this one here and this one. So if you look, 1, 2, 3, 4, 5, 6, 7, 8 different chiral carbons. So there would be 2 to the 8th is the maximum number of stereoisomers. But there's only one cholesterol, and this molecule is synthesized in your body, and it always looks like this. So there's not like there might be a lot of stereoisomers, but there's only one naturally occurring. To have different steroids, what happens is these substituents change. So this will be different, and there might not be a double bond here, and this R group changes. And so that's how you will get different steroids, testosterone, estrogen, different kinds of cholesterol, by changing the different groups. But the 5-membered ring structure is always the same. And of course, if you have a 6-membered ring, you have a chair. So it's always fun to draw. I think it's fun to draw the chairs. Here's that methyl group. So if the methyl group is up, that means the next chair starts with an equatorial position. Right there is our double bond. Here is the OH. It is equatorial. The next one is going to be here. Since this is going up, we're going to have to draw an equatorial here. So at this position right here, you have a down hydrogen, a hydrogen that's in the axial position. So there's our 3 chairs. Now, when we get to this position, you have a methyl group going up. So the 5-membered ring will go equatorial down. And then this right here will be equatorial up. And that's how you would draw a 5-membered ring. 1, 2, 3, 4, 5. And then this is coming out at you. And then that methyl group is here. And I'm just going to draw an R for the rest of that. So that is the structure of cholesterol drawn as chairs. So one of my trick questions on one of my tests is how many stereoisomers are there, how many diastereomers are there of cholesterol? Well, the answer is 2 to the 8th minus 2. Why minus 2? Because 1 is cholesterol and 1 it's enantiomer is equal to the number of diastereomers of cholesterol. And the other nasty question I do is I make, for bonus points, make everybody, or they don't have to, it's bonus points, find the R's and S's on all the chiral carbons, which takes a lot of time and it's a good time killer, but it's a great way to earn some bonus points. So if you have some extra time, play with the R's and S's on this molecule.